Welcome to this new episode of Pacta Industry, where we introduce you to the Siroco cable harness crimping tools, distributed in France by Cotelec. With more than 30 years of experience, Siroco has become a trusted name in the cable and harness industry. The company designs and manufactures certified tools, devices, and machines that can be fully customized to meet the most demanding requirements. By using high-quality materials, Siroco ensures precise machining, reliable performance, and long-lasting durability. On top of that, their commitment to agile technical support makes them a reliable partner for your projects. To learn more, visit Cotelec's website and get in touch with their engineers for detailed information about the complete range of Siroco crimping solutions. And don't forget to subscribe to the Pacta Industry channel, home of the Journal of Connectivity. Share our videos and activate the notification bell so you never miss the latest updates.
Welcome back to the Deep Dive, where we peel back the layers on the unseen engineering marvels that power our modern world.
It's great to be here.
Today, we're zooming in on something you interact with countless times a day, often without a second thought. The electrical connection.
Yeah, absolutely. Things we just take for granted.
Think about it. Every time you flip a light switch, plug in your phone, or start your car, you're relying on precise electrical connections. But we're not just talking about a simple plug-in. We're diving deep into one of the most critical yet frequently overlooked forms of these connections: crimping.
Right. It sounds basic, maybe,
Yeah.
but it's anything but.
Exactly. It's not merely a mechanical squeeze, it's a sophisticated science. And its unwavering reliability underpins everything from your daily commute to humanity's most ambitious ventures into the furthest reaches of space.
It's truly remarkable, isn't it? How something so small and seemingly straightforward can be so profoundly complex and universally important, yet remain entirely invisible to most of us.
Absolutely. And that's our mission today, to pull back the curtain on this hidden world. Our deep dive will reveal the surprising complexity and universal importance of crimping technology.
Yeah, we're going to unpack it.
We'll explore its fundamental principles, delve into the incredibly stringent requirements demanded by environments as diverse as the automotive industry and NASA, and uncover the meticulous tools and rigorous quality assurance processes that ensure these tiny connections don't lead to catastrophic failures.
Prepare for a genuine aha moment, I think. Because what seems like a simple squeeze is actually an incredibly advanced engineering feat, keeping our modern world connected and safe.
So let's start with the absolute basics. When we talk about crimping in this high-stakes context, what exactly are we defining? What is it, fundamentally?
Okay. Well, at its core, crimping, as defined by the NASA standard, is simply a method of mechanically compressing or securing a terminal, splice, or contact to a conductor.
Okay, compressing, securing sounds straightforward.
But what's critical here, and often overlooked, is that it's about creating both an electrical and a mechanical connection simultaneously. It's not enough for the wires to just touch, Really? They need to be physically locked together in a way that guarantees consistent long-term performance.
That sounds pretty straightforward on the surface, like just squeezing metal around a wire. But you're telling me it's far beyond just simple compression, right? There's a lot more going on at a microscopic level.
Precisely. It's an intricate process where the contact material is deformed around the conductor to establish what we call a gas-tight interface.
Gas tight. What does that mean exactly?
Imagine two metal surfaces pressed together so tightly that no air or moisture can penetrate between them at the contact points. This mechanical compression creates a very specific interlock between the conductor's individual strands and the contact material itself.
Oh, okay.
It ensures a robust, consistent performance over time. It's essentially about cold welding those materials together without actually using heat.
Cold welding. Okay, that's a great way to put it. So if crimping is this sophisticated, why has it become the undisputed go-to method? Historically, soldering was king for electrical connections, wasn't it?
It was, yeah. And it's still widely used in many places.
So why the shift? Why crimping over soldering now, especially in these high reliability applications we're talking about?
Well, what's truly fascinating here, as the Crimping Technology Compendium notes, is that crimp and press connections have, and I quote, largely replaced soldered connections and proven themselves over the years as state-of-the-art connections.
Largely replace.
And this shift isn't just a matter of preference or convenience. It's driven by fundamental material science, particularly when it comes to copper, which is, the most common conductor material.
And here's where it gets really interesting because it has to do with something as common as rust, or rather oxidation. You mentioned copper. Can you unpack the copper oxide challenge for us? What makes it such a problem for electrical connections?
Certainly. Copper, when exposed to air, and that's just about always naturally oxidizes, almost immediately a firmly adhering and durable oxide layer of about 2 to 4 micrometers forms on its surface.
2 to 4 micrometers, that's incredibly thin. How thin is that compared to, say, a human hair?
Right. To give you a sense, a human hair is roughly 50 to 100 micrometers thick. So we're talking about a layer many, many times thinner than a single strand of your hair.
Wow.
And this layer changes color. You might notice it sometimes. It goes from a shiny orange-reddish shade to a matte dark brown, depending on the degree of oxidation and exposure. But the crucial detail and the challenge is that this layer is electrically insulating.
Electrically insulating. So if you just press a wire with this layer into a contact, you're essentially putting a microscopic insulator between the connections.
Exactly.
Which would cause increased transition resistances. That's a significant problem for conductivity, obviously. It's like trying to make a circuit with a tiny piece of plastic in the way.
That's exactly right. And this is where the ingenious solution of the crimp comes in. The crimping process is specifically designed to overcome this insulating oxide layer.
How does it do that? Just by sheer force?
Not just force. Due to the irregular pressing of the stranded conductor during crimping, this oxide layer is actively and microscopically broken up. The deformation isn't just about simple compression. It's about a complex interplay of forces.
Okay.
These forces cause the individual strands of copper wire and the metal of the crimp contact to cold flow and interlock. Think of it like a perfectly meshed gear system, but on a microscopic level.
Like tiny teeth locking together.
Precisely. The crimp doesn't just squeeze, it deforms the wire in contact in a way that creates a multitude of tiny interlocked surfaces, almost like molecular keys fitting into locks. This combination of friction and physical interlock creates what's called a friction-locked and keyed permanent connection with good electrical properties.
Friction-locked and keyed.
This is the core science, ensuring direct metal-to-metal contact where it counts, reliably, every single time. If you were to look at a micrograph, essentially an autopsy slice of a poor crimp, you'd see more cavities and undeformed individual strands.
And that means trouble.
Exactly. This translates directly to worse electrical and mechanical properties and even allows moisture to penetrate, leading to pitting corrosion, where tiny holes form and degrade the connection over time.
So it's not just holding the wire, it's physically scrubbing away that insulating layer and creating a molecular bond. That's a far cry from a simple squeeze. What does this all mean for the ultimate objective of crimping technology? Clearly, it's about ensuring quality, but there's a delicate spectrum to that, right? Not all errors are created equal.
Right. The overarching objective is to produce consistently high-quality, reliable connections every single time. This requires a meticulous assessment of the results of the individual work step.
Meticulous assessment, okay.
And the compendium highlights the critical difference between a critical error and a tolerable error, which is a really insightful distinction.
Critical versus tolerable. Give us an example.
Okay, so for instance, a missing rear bell mouth, that's the little flare at the back of the crimp, is classified as a critical error. It's explicitly labeled as bad and must not be used.
Why is that so bad?
Because it creates an immediate inherent weak point that guarantees failure under stress or vibration. It's not just suboptimal, it's structurally compromised right from the start.
Whereas a tolerable error might be something like an insulation crimp over-crimped. It's not ideal, maybe it doesn't look perfect.
Exactly.
But it doesn't immediately compromise the fundamental electrical or mechanical integrity in the same catastrophic way. This really emphasizes the spectrum of acceptable quality and why careful workmanship is so crucial, knowing what crosses that line from not perfect to, potential failure.
Indeed. It also speaks to the importance of farm maintenance for the crimp itself. This is especially true for open crimp barrels, which are formed from sheet metal.
Form maintenance, you mean keeping its shape?
Yes, precisely. Materials naturally tend to spring back into its original shape after the bending process. Think about bending a paperclip. It always springs back a little.
Sure.
To counteract this and maintain that critical friction-locked and keyed connection over time, the crimp flanks must touch and support each other. Without proper support and interlock, the material's tendency to spring back could gradually loosen the connection, leading to increased resistance, heat, and ultimately failure. It's a constant battle against the physics of materials.
All right, so we understand the intricate science behind a good crimp. Now let's talk about where this science becomes absolutely non-negotiable, where compromise simply isn't an option. We're moving from the microscopic details to the cosmic, starting with NASA's golden standard for crimping, especially for spaceflight hardware.
Yeah, this is where the stakes, they just don't get any higher.
When lives are at stake and even billions of dollars hang in the balance, what does it take? What's the standard?
We're talking about NASA STD 8739.4A. It's a critical technical standard, approved back in 2016, which sets forth the detailed requirements for interconnecting cable and harness assemblies that connect electrical, electronic, or electromechanical components.
So, the rulebook for wiring in space.
Pretty much, yeah. This document isn't just a guideline, it's the Bible for reliability when it comes to any wiring used in space missions.
And its applicability isn't just for any piece of equipment, is it? It's specifically for spaceflight hardware or mission-critical ground support equipment.
That's right. Very specific.
Can you give us a clearer, almost visceral picture of what critical work means in NASA's eyes? Because I imagine the consequences of failure are pretty severe.
They are astronomical, you could say. And the standard defines it in no uncertain terms. Critical work refers to any task where incorrect performance risks a catastrophic outcome.
Like what specifically?
Such as loss of human life, serious injury, loss of a Class A, B, or C payload. Those are the most expensive and important missions, you know.
Like the flagship ones?
Also, loss of a Category 1 or Category 2 mission, or loss of a mission resource valued at greater than $2.
$2 million. Just for one resource failing because of potentially one bad connection.
Exactly. To put it plainly, if an improperly made crimp leads to a $2 million piece of equipment failing, or worse, impacts crew safety, it's critical work. This immediately establishes the extreme demands placed on every single connection, from the largest cable harness to the tiniest wire. The consequences of failure are simply unacceptable.
So with those kinds of stakes, it's clearly not just about the crimp itself, but a holistic approach to ensuring reliability. What are the foundational principles of reliable cabling that NASA emphasizes?
You're absolutely right. It's systemic. The standard outlines fundamental factors that create a comprehensive ecosystem of reliability. Proper design, control of tools, materials, work environments, and careful workmanship by trained and certified personnel.
Design, tools, materials, environment, people. Got it.
It's a systemic approach, recognizing that a chain is only as strong as its weakest link, and every single link must be perfect.
Let's talk about design practices and material selection. What kind of wire are we talking about here, and are there any specific prohibitions that might surprise people?
Okay, first, crucially, stranded wire shall be used for crimping.
Stranded, not solid. Why?
Because stranded wire is flexible and can deform optimally during crimping to create those microwelds we discussed earlier. The standard explicitly prohibits crimping of solid wire.
Right, it's too rigid, it might crack.
Exactly. Solid wire doesn't deform consistently, and it's prone to breaking with vibration, which is obviously a huge factor in spaceflight. And notably, crimping of solder tin stranded wire is prohibited.
Wait, tinned wire is prohibited. Why? Doesn't tinning help with soldering?
It does for soldering, but for crimping, tin wire can suffer from something called cold flow. Think of it like very slow motion squishing.
Cold flow. Explain that.
Okay, imagine continuously pressing on a softer material, like the solder tinning on the wire. Over time, even without heat, it will gradually deform and flow away from the pressure point. In a crimp, this cold flow would mean the connection slowly loosens, becoming unreliable and potentially dangerous as the contact pressure decreases.
That makes perfect sense. So you need the bare copper strands. What about very fine wires?
Good question. For smaller conductors, specifically AWG24 and smaller, high-strength copper alloys shall be used to ensure mechanical integrity despite the fine gauge. You need that extra strength.
Okay. You don't want rigidity where flexibility is needed, or material that will slowly lose its grip. And for space, materials must have properties far beyond what we'd consider for everyday use. What are some of those specific considerations for wire insulation, lacing tape, and braid sleeving?
Oh yeah, the materials are critical. For space applications, the properties are paramount because they have to survive an incredibly harsh environment. We're looking at attributes like processability, basically, how easily it can be worked with.
Right.
Flammability, which is obviously crucial in a closed, oxygen-rich environment sometimes. arc tracking resistance to prevent electrical shorts,
Makes sense.
and critically, vacuum stability. This means the materials cannot outgas, release gases in the vacuum of space,
Outgas. Why is that bad?
because those released gases could condense on sensitive optics, like telescope lenses or sensor windows, or interfere with electronics. So no outgassing allowed. And of course, resistance to cold flow for insulation materials too, as insulation that deforms over time could expose conductors.
So these materials are chosen not just for electrical performance, but for surviving space itself.
Precisely. It's an extreme, unforgiving environment.
Beyond the material itself, there are strict requirements for physical integrity, like bend radii. It's not just about getting the wire from point A to point B, but how it gets there. What are some examples of those, and why are they so specific?
Yeah, the routing is key. The standard specifies incredibly precise bend radii to prevent wire damage, which could lead to signal degradation or outright failure.
Like how precise?
For instance, an individual coaxial cable has an optimum bend radius of 10 times its outer diameter, OD, and an absolute minimum of 6 times its OD.
10 times. So a cable that's, say, 2 millimeter thick needs a bend radius of at least 12 millimeters, preferably 20 millimeters.
Exactly. This precision prevents internal wire damage, like microfractures or changes in impedance, ensuring signal integrity. Wires exiting connectors also require stress relief, specific ways to support the wire so vibration doesn't fatigue the connection point.
Makes sense.
And overall, entire harnesses must be meticulously protected from abrasion, cold flow, cut-through, vibration, chafing, flexing, and sharp edges. Think of it as protecting the nervous system of a spacecraft. Every nerve fiber is vital.
And preventing mismating of connectors is also a huge deal, I imagine. You can't just plug things in randomly up there, where mistakes can cost millions or lives.
Oh, absolutely. Even a perfect connection is useless if it's plugged into the wrong port. Techniques like using different connector sizes, clear polarization keys so they only fit one way.
Like a USB-C connector, almost.
Kind of, yeah, but often much more robust. Also, distinct clear marking or even confidence loop circuits, which are electrical checks built in to verify proper mated positions, are mandated to prevent catastrophic errors. It's about designing out the possibility of human error at every stage.
So we've got the design and materials covered, the physical integrity, safeguards against mismating, but all this relies on actually making the connections. What about the tool and equipment control? These aren't your average pliers from the hardware store, are they?
Far, far from it. Tools must be appropriate to the intended function, always cleaned and properly maintained, and thoroughly examined for physical damage before every single use.
Every use.
Every use. Any defective or uncalibrated tools are strictly prohibited in the work area. This isn't just a suggestion. It's an absolute mandate because even a tiny imperfection in a tool, like a worn indenter, can translate into a critical flaw in a connection.
And calibration is key here. I'm guessing close enough simply isn't an option.
Absolutely not. Zero tolerance for close enough. There must be a documented calibration system following recognized standards, like ANSI CSL Z540 6 nan to 1 1994. Everything needs traceability to NIST, the National Institute of Standards and Technology.
So you can prove its accuracy.
Precisely. Defined calibration intervals, clear labeling indicating the date of calibration, the next due date, and any limitations of use. This creates an auditable record, ensuring that every tool used is performing exactly within its specified parameters. It's a painstaking process, but essential for absolute reliability.
What are the specifics for the crimping tools themselves, the ones actually performing the crucial squeeze? What makes them special?
Okay, NASA requires crimping tools to have a full-cycle ratcheting mechanism.
Ratcheting. Why is that important?
It's vital because it prevents the indenters, the parts that do the squeezing, from releasing before the crimp cycle has been completely finished. It forces a full, proper crimp every single time.
No half measures.
Exactly. No partial crimping allowed. They also need a minimum of 4 indenter blades, preferably double indenter blades, to ensure even radial compression from all sides, not just squashing it flat.
4 points of contact. Okay.
And for any adjustable tools, they shall be set, sealed or locked, and verified prior to use to prevent any unauthorized changes or accidental misalignments during use. Everything is locked down.
This all sounds incredibly rigorous, but even with the best tools and designs, there's always the human factor. How does NASA ensure personnel are not just capable, but consistently up to these incredibly high standards?
Right. The people are just as critical as the tools. This is where the training and certification program comes in. The supplier is responsible for maintaining a documented training program, a comprehensive system designed to ensure every individual involved is proficient.
Operators, inspectors?
Yes, certifying operators, inspectors, and instructors to specific levels. For example, the standard mentions Level A NASA instructors and Level B supplier instructors who provide this critical, highly specialized training. It's a tiered system to ensure knowledge transfer and adherence to standards right down the line.
What are some of the rigorous requirements for these personnel? I heard there are even vision requirements, which makes sense for such detailed work.
That's right. Personnel must meet specific vision requirements every 2 years, administered by a qualified eye examiner. Imagine trying to spot a microscopic flaw or a tiny strand of misplaced wire if your vision isn't absolutely perfect.
Good point.
And recertification is mandatory every 2 years, or sooner if new techniques are introduced, if work is interrupted for more than 6 months, or if quality is deemed unsatisfactory. Certification can even be revoked for failing recertification or not meeting vision standards.
So it's not just a one-time course.
No way. It's a continuous, demanding process of proving and reproving competence. It's not a one-and-done thing. It's a career-long commitment to excellence and meticulousness.
And where does this elite training happen?
Well, the training of Level B instructors, for example, is available at the NASA training centers, specifically the Goddard Space Flight Center and the Jet Propulsion Laboratory. They also provide the NASA generic crimping, cabling, and harnessing training plan. These aren't just classrooms. They are hubs of expertise where the most meticulous standards are taught and upheld.
Okay, so once everything is built, the people are certified, the tools are calibrated. How does NASA ensure quality and test these connections? Is it a trust but verify situation, or more like verify then verify again?
It's definitely the latter. Verify, then verify again. And again, crimped connections shall be inspected 100% to verify compliance.
100% inspection. Wow.
And this isn't just a final check. There's a crucial pre-crimp examination where crimped contacts are inspected before any wire insertion.
Before you even start, what are they looking for?
Inspectors meticulously look for any tiny flaws. Cracks in the plating or base metal, tarnishing or discoloration, plating removal or flaking, out of roundness or exposed base metal. You're checking the raw materials for perfection even before the process begins. Any doubt, it's rejected.
So they check the components before they even start assembly, which makes perfect sense. And then there's actual physical testing, like tensile strength testing. This sounds like the ultimate stress test, pulling it apart.
Exactly. This is a crucial production quality control test. It's performed at the start and at the end of each work shift or production run, whichever is shorter.
Start and end of every shift.
Yes. It requires a minimum of 3 test samples. And critically, production can only proceed if there are 0 failures out of 3 samples tested.
0 failures. So if even one sample fails,
The entire batch produced since the last successful test is suspect. And the process must be stopped, investigated, and reevaluated. You can't move forward until you pass.
what does that test look like in practice? What kind of forces are we talking about? Are these wires easy to pull out?
Not if the crimp is good. The test involves a tensile testing device that pulls the wire straight out of the crimp assembly at a specific controlled head travel speed, 25.4 minutes, 6.3 millimeter, 1.00, 0.25 inches per minute. Slow and steady.
And the forces?
There are specific crimp tensile strength values that must be met, and they vary significantly depending on the wire gauge. For example, an AWG-28 wire, which is quite fine, needs to withstand a 22 newtons 5 pounds minimum pull force.
5 pound, like a small bag of sugar, maybe?
Roughly, yeah. But for a larger AWG-12 wire, that jumps significantly to 459 newtons to 103 pounds minimum.
Oh, for 100 pounds, that's like trying to lift a heavy suitcase by a single wire.
Exactly. It has to be incredibly strong. They even categorize crimp joint tensile failure categories, using illustrations to diagnose how a failure occurs. Did the wire break? Did it pull out? Not just if it occurs. This helps pinpoint the root cause if something does go wrong.
And what about the small but critical details, like the gap between the wire insulation and the crimp barrel? I imagine that's precisely controlled too.
Oh, absolutely. Millimeter precision matters everywhere. Insulation clearance is precisely specified. For AWG-20 wires and smaller, the acceptable clearance is a tiny 0.25 millimeter to 0.75 millimeter.
Less than a millimeter.
Yes, this ensures proper termination. You don't want insulation getting caught in the electrical crimp area, as that would compromise the connection. But you also don't want too much bare wire exposed between the insulation and the crimp, which could lead to shorts if it touches something. Every single detail is controlled.
Incredible. Now, if we connect this to the bigger picture, it's not just rockets and spacecraft that demand this level of precision and unwavering reliability. The automotive industry also faces incredibly high stakes, albeit closer to home.
That's a crucial point, yeah. And it's why our deep dive highlights this universal demand for quality. Well, we've just spent a lot of time orbiting Earth, metaphorically speaking.
Right.
Back on the ground, the automotive industry demands similar criticality for safety on the road. The Crimping Technology Compendium explicitly lists safety-critical applications like ABS, anti-lock braking system, airbag, emergency call systems, alongside aviation and medical equipment. These are literally life-saving systems that rely on these tiny connections working perfectly every time.
Absolutely. Your brakes failing or your airbag not deploying because of a bad crimp, unimaginable.
And what's fascinating here is that the cost of failure translates into very real-world impacts that affect millions of people. We regularly hear reports of recall actions in the automotive industry, house fires due to short circuits, etc.
Yeah, those recalls can cost manufacturers millions, right?
Easily. This underscores that the follow-up costs in case of a failure of, e.g., a crimp connection, may be many times higher than the initial cost of implementing stringent quality control. A few cents saved on a crimp could cost a manufacturer millions in recalls, damage brand reputation, or worse, cost lives.
So it's a truly universal quality demand. Regardless of the industry, if human safety is on the line or critical functionality is required, the requirements for these connections are similarly stringent. It's not just NASA being, extra careful. It's a global understanding of what defines reliability.
Absolutely. Quality standards in crimping and pressing technology are becoming ever more stringent across the board. If a harness maker wants to be approved as a supplier for automotive, aerospace, or medical,
They have to meet these standards.
exactly, they must meet these high standards with his processing equipment and testing methods. This is not just about compliance checkboxes. It's about preventing catastrophic outcomes and ensures consumer safety and trust.
This also raises an interesting debate around wire preparation. The compendium touches on the pre-treatment debate for conductors, referencing the VDE 0100 Severdauer 520 standard. Can you explain that, especially as it relates back to things like cold flow?
Certainly. This specific standard, for instance, strictly prohibits soldered stranded compounds in screw terminals
Soldered wires and screw terminals.
because of the risks of cold flow and subsequent connection failure. Remember our analogy of slow motion squishing?
Yeah, the solder moving under pressure.
Right. If you solder the end of a stranded wire to keep the strands together, the solder fills the gaps. When that tinned wire is then put into a screw terminal and tightened down, the solder, being a softer metal, can gradually deform and flow away from the pressure point over time, even at room temperature.
So the screw becomes loose.
Essentially, yes.
Yeah.
This cold flow reduces the contact pressure, loosens the connection, and can lead to increased resistance, overheating, and eventually failure. Could even cause a fire in some cases.
Wow. So the debate is whether you should use unprepared conductors, just cut and stripped, versus prepared ones, maybe with a ferrule crimped on.
Exactly. A ferrule is a small metal tube crimped onto the end of the stranded wire. It contains the strands and provides a solid cylindrical surface for the screw terminal to clamp onto, preventing cold flow issues associated with solder. Manufacturers of terminal blocks must specify if pre-treatment like using a ferrule is necessary. It reinforces that even seemingly simple connections have layers of engineering thought behind them to prevent these slow, insidious failures.
Okay, so we've established the critical importance of crimping, from the intricate science-breaking oxide layers to the non-negotiable standards demanded by industries like aerospace and automotive, where failure is not an option. Now, let's turn our attention to the actual process, the precision toolkit, and the meticulous steps used for making and verifying these connections. And it all starts at the very beginning. Wire preparation.
Indeed, the first critical step is preparing the wire, specifically stripping the insulation off the end. It seems simple, right? Just remove the plastic.
Seems like it, yeah.
But it's fraught with potential for damage. As the NASA standard outlines very clearly, the tools shall not nick, ring, gouge, or stretch conductors, or remove plating so that the base metal shows.
Nick, ring, gouge, stretch. Lots of ways to mess it up.
Absolutely. Even superficial scraping is only acceptable if the base metal remains covered by its plating, as any exposed base copper could lead to corrosion or a weaker connection point. The precision required right from this first step is astounding.
And a bad strip can completely ruin the integrity of the connection before you even get to the crimping stage, right? Which means all that subsequent effort is basically wasted.
Totally wasted.
Yeah.
The compendium gives us some really clear visual examples of good versus bad stripping. What differentiates them is pretty stark when you see it.
What does good look like versus bad?
Okay, a stripping OK example shows all the individual wire strands present and undamaged. Crucially, the insulation is cleanly cut, revealing the full conductor cross-section without any straggling bits of insulation or damaged strands. In contrast, bad stripping includes horrors like individual wires damaged and attador cut off. Imagine losing precious strands of conductivity right there. Or single wire pulled, longer than the others. Or the surface of single conductor strands scratched on one side. Even insulation improperly cut, leaving little insulation threads that can get caught in the crimp.
Insulation threads. That sounds like exactly what you don't want in an electrical connection.
Exactly. These seemingly minor issues can lead to poorer electrical properties and increased contact resistance in the final crimp, undermining all the other quality efforts. It's like building a skyscraper on a cracked foundation. It's just not going to hold up.
So the type of blade used for stripping really matters. I understand V-stripping blades in hand strippers are preferred over straight blades. Why is that the case?
Good point. Straight blades are problematic because they tend to crush the insulation before cutting it, which can cause uncleanly cut frayed insulation and those dreaded insulation threads we just talked about.
Right, the little bits that get caught.
Yeah. Imagine tiny strands of plastic or rubber getting caught right in the metal crimp that creates an insulating barrier where you absolutely need pure metal-to-metal contact. This leads directly to poorer electrical properties and increased contact resistance. V-stripping blades, in contrast, use a shearing action, providing a cleaner, more precise cut that minimizes these issues, creating a perfect canvas for the crimp.
Makes sense. And even something as subtle as dwell time and blade sharpness plays a role. This sounds like micromanagement of the stripping process itself.
It kind of is, but it's necessary micromanagement.
Yeah.
The type of insulation material, whether it's harder like Teflon or softer like PVC, directly affects the dwell time required for the blade to properly cut through without nicking the conductor underneath.
Softer insulation needs more time.
Often, yes, a slightly longer dwell time for a clean cut without tearing. And naturally, dull blades' worsen cutting properties require longer dwell times and can start to damage wires. This impacts production speed and, more importantly, quality. Regular monitoring of stripping results is crucial for maintaining blade sharpness and optimizing the process. It's a constant battle against tool wear and tear.
Okay, so after the wire is perfectly stripped, pristine condition, we have to choose the right crimp connection type. This sounds like an assignment problem you've mentioned before, where it's not just a generic choice like picking any old screw.
It truly is a precision assignment problem. You have to get the match exactly right. The compendium highlights that for an optimal crimp connection, the entire system, the crimp contact plus wire plus crimp tool setting, must all be perfectly matched and validated.
So you can't just grab any contact that fits the wider size.
Well, you can, but you shouldn't if you want optimal results. It explicitly warns against using crimp contacts designed for several cross-sections or cross-section ranges. A contact might be listed in a catalog for, say, 0.5 to 1.5 square millimeters.
Right, a range.
But it might only be truly optimal, meaning it gives the best possible electrical and mechanical performance for maybe 1.0 square millimeters. Using it at the extremes for 0.5 or 1.5 could result in suboptimal or poor crimp connections, even if you technically follow the catalog data for tool settings.
Even if the manufacturer says it's okay.
The compendium implies you need to verify. It raises an important question. Why compromise on quality? And it states definitively, always check crimp connections via micrographs, especially during development and setup.
That's a critical insight for anyone in manufacturing or design. It's not just about what fits, but what's optimal for that specific combination to achieve peak performance and longevity. Let's quickly overview some of these diverse crimp connection types, starting with the ubiquitous open crimp barrels. What are those?
Okay, open crimp barrels are very common. They're formed from a flat strip of metal, usually brass or phosphor bronze, that is then folded around the wire during the crimping process. They're commonly used with wire cross-sections up to approximately 50 square millimeters.
And they have that feature you mentioned earlier, the bell mouth.
Yes, a key feature here is the bell mouth rear, which is that flared, funnel-like opening at the back of the crimp barrel where the insulation ends. This bell mouth is absolutely essential because it prevents a predetermined breaking point.
How does it do that?
It provides a gradual transition in stiffness from their rigid, crimped conductor section to the flexible, insulated part of the wire. Without it, that sharp transition point would be a major stress concentration, leading to premature wire fatigue and breakage, especially under vibration.
Got it. And there's a whole array of specific crimped shapes, even within open barrels, each designed for a particular application. It's definitely not one size fits all.
Indeed, engineering is all about specificity, matching the form to the function. We have the BF crimp, which is kind of the standard shape for open crimp sleeves, suitable for wires up to about 50 square millimeters. It forms a sort of B or F shape in cross-section when viewed end-on, wrapping tightly around the wire strands.
Okay.
Then there's the O crimp. This is often an open claw form used for wire and ferrules, those little tubes we talked about, to bundle and fix individual stripped wires neatly, typically up to 6 square millimeter, just makes a nice round bundle.
Right.
For gripping the insulation itself, not just the wire, we see the OV crimp. Here, OV stands for overlap. It's commonly used for wires with reduced insulation thickness, providing a secure mechanical grip on the insulation without damaging the wire inside.
Gripping the insulation, too. Interesting.
Yeah, it adds strain relief. There are also O crimps that can be asymmetric or symmetric, again used for installation crimps. These are often used to fix single wire seals for weatherproofing connectors, or again for wires with reduced insulation thickness, ensuring everything stays put and sealed.
And one more.
Finally, the roll crimp is typically used for uninsulated flag terminals, those flat ones that stick out at 90 degrees. It creates a specific low profile but strong connection. Each shape really serves a specific purpose, designed for optimal performance given the wire type, the insulation, the terminal design, and the application. It's all about balancing mechanical grip, electrical conductivity, and sometimes insulation support or sealing.
What about closed crimp barrels? These sound like they're maybe for even more demanding situations, perhaps environmentally sealed applications.
Often, yes, or where maximum robustness is needed. For closed barrels, the crimp contact starts as a complete tube or barrel before the wire is inserted, offering potentially greater protection and perhaps more consistent radial compression.
What kinds of crimps are used with those?
We see the indent crimp, which is common for tubular cable lugs and connectors, or ring and pin type terminal ends used in heavy-duty applications. This uses one or more pointed dies, or indenters, to press deep indentations into the barrel, forcing the metal to flow around the wire strands.
Like dimples pushed in.
Exactly. Another very effective option, especially for ferrules again, is the hexagonal crimp. This uses multiple dies to form the barrel into a hexagon shape around the wire. It's space-saving and produces optimum contact in narrow, round terminal blocks, providing excellent uniform radial compression around the wire bundle. It's very popular for ensuring all individual strands are evenly compressed and making good contact.
And then there are turned contacts, which sound like the absolute top tier, machined with incredible precision, not just stamped.
Turned contacts are indeed the premium choice, the Rolls-Royce of crimp contacts, if you will. They are machined from solid metal rod, not stamped and formed from sheet metal. This makes them incredibly precise, dimensionally, and very durable.
And always closed barrel.
Yes, they are always the closed barrel type. They are primarily used in the highest quality, highest reliability applications, such as military, aerospace, medical, automotive industries. Anywhere, consistent performance is absolutely paramount, and cost is secondary to reliability.
What's their key advantage?
Their key characteristic is that their precision leads to consistent crimp quality guarantees constant contact resistance. There's less variability than with formed contacts. For these, it's also vital to ensure proper insulation fixation or structural protection, often through the connector housing itself, against any mechanical loads, because the contact itself is usually just focused on the electrical connection. They're designed for situations where failure is simply not an option.
Okay, this raises an important question. How do you actually ensure all this precision, especially when you can't always see inside the crimp, to check that crucial metal-to-metal contact we talked about? This brings us to the pillars of quality assurance. Beyond visual inspection, what are the key methods?
Right, this is truly the bedrock of reliability. You can't just assume it's good. There are 5 basic test methods outlined in the compendium, and it's essential to understand a key insight they provide. Each test method on its own is not sufficient. Only the combination of these test methods enables the production of consistently high and reproducible quality.
Not sufficient on its own? So you need multiple checks. What are the 5?
They are visual inspection, measurement of crimp dimensions like height and width, the pull-out test for mechanical strength, micrograph plus micrograph evaluation for internal structure, and crimp force monitoring during the actual crimping process.
Okay, 5 pillars.
Exactly. They complement each other, forming the indispensable backbone of any serious quality assurance program for crimping. No single test tells the whole story. You need the combination.
Let's circle back to visual inspection, which seems like an obvious first step, but also incredibly important, especially if you know what you're looking for. What are you checking with your eyes?
Visual inspection is indeed one of the most important tests because it's fast, it's non-destructive, and it can catch many obvious flaws immediately. Inspectors are trained to check for things like the cutoff tabs, those small bits of metal sheared off from the contact strip during crimping. They should be visible, but no longer than 0.5 millimeter typically. They look for no insulation damage, though minor pressure marks might be allowed, ensuring a correctly positioned seal if it's a sealed connector, and that the crimp contact overall is straight and not bent. A bent contact might not mate properly or could indicate uneven crimping forces.
So training is key here.
Absolutely. Training personnel where to look and how to look correctly is paramount. Subtle flaws, like a slightly bent terminal uneven bell malformation or an incorrect cutoff tab length, can indicate significant underlying problems with the tooling or setup that could lead to electrical or mechanical failure down the line. It's about recognizing the visual warning signs.
Next, measuring crimp dimensions. What's the key measurement here, and why is it so reliable for ongoing quality control during production?
The primary adjustable and measurable dimension, the one most often checked, is crimp height. This is the final height of the crimped wire barrel. Measuring it is a quick, non-destructive test that offers reliable quality control during ongoing production.
How precise does it need to be?
Incredibly precise. For a very small wire cross-section range, like 0.03 to 0.20 millimeters, the tolerance on the crimp height might only be plus minus 0.02 millimeters.
0.02 millimeters, that's what? Thinner than paper.
Yeah, roughly the thickness of a thin plastic film or a couple of human hairs. Measuring tools like specialized micrometers or calipers with special grinding on their jaws to fit the crimp shape are designed to ensure consistent measuring pressure, as even slight variations in how you measure could throw off such a tight reading. A quick, quantifiable check that confirms the crimp tool is set correctly and performing consistently throughout a production run.
Then there's the pull-out test, which we mentioned NASA uses extensively, but it's clearly a universal standard. This is where you physically test the mechanical strength, right? You pull it until it breaks.
Yes, the pull-out test, using a calibrated tensile testing device, directly measures the mechanical strength, the holding force, of the crimp. The force is applied slowly and steadily along the longitudinal axis of the contacting conductor until failure occurs. Either the wire breaks or it pulls out of the crimp.
And this tells you.
The result, the peak force it withstood, is absolutely critical in validating both the crimp tool setting, ensuring it provides sufficient mechanical grip, and the overall quality of the connection. If it can't withstand the specified minimum force for that wire size and contact type, it fails. This indicates an underlying problem with the crimp's integrity, perhaps insufficient compression or strand damage, which directly translates to its ability to survive vibrations and physical stress in a real-world application.
And for a true autopsy of a crimp, for a deep dive into its internal structure, you turn to micrograph and micrograph evaluation. This is where you really see the unseen, isn't it? Cutting it open.
This is perhaps the most revealing test, and indeed it's usually destructive. You can't easily put the crimp back together after this. It involves carefully cutting a precise cross-section through the crimp, embedding it in resin, polishing it to a mirror finish, and then examining it under a powerful microscope, often after etching it to reveal the grain structure.
What does that cross-section show you?
What it reveals is the internal structure that no other test can show. You can directly see how tightly the individual wire strands are compressed, how much they've deformed and cold welded together, how well they've filled the available space inside the crimp barrel, and how they've interlocked with the material of the contact itself.
And you can spot problems easily.
Oh, yes. The insight here is clear. More cavities and undeformed individual strands mean the worse the electrical and, of course, the mechanical properties. You want to see a solid mass of deformed copper, minimal voids. It also clearly shows if moisture can penetrate through gaps, potentially leading to pitting corrosion over time. It's also crucial for identifying issues like overfilled contacts, where the wire cross-section is simply too large for the crimp barrel causing damage, or too large contacts where the crimp flanks are rolled in too far, indicating improper tool setup.
So it's not just for troubleshooting after a failure happens, but essential during initial development and validation, ensuring you've got the perfect recipe for that specific wire and contact combination.
Precisely. It's absolutely essential during the assignment of the nominal cross-section of the wire to the crimp contact within the scope of development, and applies in general to all crimp contact types. The compendium warns, quite starkly, that if this detailed micrograph analysis isn't done properly in the development phase before mass production begins, it's almost inevitable that suboptimal or poor crimp connections are produced.
Even if they pass the other tests.
Even if they seem okay visually and pass the pull test initially, the micrograph reveals the long-term reliability potential. This is why that assignment problem we discussed earlier, ensuring the perfect match of wire, contact, and tool, is so fundamentally important. The micrograph is the definitive judge of whether you nailed that match.
Okay, pillar number 5, crimp force monitoring. This sounds like real-time quality control, almost like an immediate heartbeat check on every single crimp as it's being made.
That's the exact philosophy behind it, the prompt detection of faults during the actual production process. It aims to make automated good, not good decisions for each individual crimp connection as it happens, in milliseconds.
How does it work?
This advanced technology typically uses piezoelectric force sensors built into the crimping press or applicator. These sensors measure the rapidly changing force variables in the millisecond range during the crimp cycle, generating a unique force versus time, or force versus displacement curve. The systems typically measure forces from a few 100 N to about 40 kN, depending on the application.
And a good crimp has a recognizable signature.
Exactly. These sensors are incredibly sensitive to the distinct force signature or profile of a perfect crimp for that specific wire and terminal combination. The system learns this signature and then compares every subsequent crimp against it in real time.
What kinds of faults can this real-time monitoring detect immediately, potentially stopping a production run before it creates thousands of faulty parts?
It's crucial for detecting subtle but critical issues like missing individual strands in the conductor, cross-section changes, which result in a lower peak force. A telltale sign the wire wasn't stripped correctly or wasn't fully inserted. It can often spot insulation crimped in the wire crimp, which would change the force profile significantly. And it can even detect broken wear parts in the tooling itself, like a chipped anvil or indenter, which would also alter the force signature. So it's like an early warning system. Exactly. However, it comes with a caveat. The crimping machine and crimping tool must be 100% okay for the monitoring to be reliable. It needs to be properly set up and calibrated, and its use is always associated with additional maintenance. You have to maintain the sensors and the system. It's a sophisticated guardian, but it needs to be well maintained itself to be effective. It's not a replacement for the other tests, but a powerful addition.
Okay, so after all these meticulous quality checks, what about the actual tools of the trade used to perform these precise operations, ranging from hand tools maybe used for repairs or prototypes, all the way up to fully automated factories?
Right, there's a whole spectrum. At one end, for lower volumes or specialized tasks, you might have stripper crimpers. These are often semi-automatic benchtop machines that combine the stripping and crimping processes into one work cycle.
What's the advantage there?
The main advantage is ensuring optimal positioning of the stripped wire in the crimp contact. After stripping, the machine holds the wire perfectly aligned and inserts it into the contact before crimping. This is particularly helpful for smaller nominal cross-sections, say smaller than 0.5 square millimeters, where manual insertion would be very difficult and error-prone. This integration significantly reduces the chance of human error in handling tiny components and ensures consistency.
And for large-scale production, where maybe millions of crimps are made daily for the automotive industry, it's all about automation, right? The ultimate in consistency and speed.
Yes, for high volume and complex harnesses, fully automatic crimping machines, like the well-known Comex Alpha and Zeta series mentioned in some literature, are the workhorses. These incredible machines handle everything, cutting the wire to length, stripping both ends, crimping terminals or contacts onto both ends, potentially adding seals, and sometimes even inserting the crimped wires into connector housings, all fully automatically. Wow. They can assemble complex multi-wire cable harnesses on integrated transfer lines. They're designed for incredible speed, unparalleled consistency, and often the flexibility to implement modifications by simply changing program parameters or swapping out individual processing modules. They really are the epitome of precision mass production in this field.
But even with all this amazing automation, there are still situations where hand crimp tools are used, maybe for field repairs, prototyping, or very low volume custom work. I imagine the same rigorous quality standards still have to apply, even without a machine's inherent consistency.
Absolutely, and this is a critical point the compendium makes. Hand tools definitely have their place, especially for maintenance, repair, or very small batches. However, the warning is crystal clear. If the work steps performed with hand tools do not meet the required quality specifications, they must not be used.
So no cutting corners just because it's a hand tool?
None whatsoever. The quality requirements do not change based on the tool, only the method of achieving them might. They emphasize the importance of using the correct hand tool for the specific contact, often requiring a correctly mounted positioning aid matched to the crimp contact to ensure the wire goes in the right place. And the tool must be capable of creating the proper bell mouth formation, just as with automatic tools. And crucially, hand tools used for critical applications, like in aerospace, must typically have that full-cycle ratchet mechanism we discussed earlier to ensure a complete crimp every time. The user's skill and diligence become even more critical with hand tools. Hashtag tag out.
So we've journeyed from the microscopic details of how copper oxidizes and creates that tricky insulating layer all the way to the vast scales of space exploration and the absolutely critical safety requirements of the automotive industry.
It's been quite the trip, hasn't it?
It really has. What we've seen is that the humble crimp connection, though often completely out of sight and out of mind, is anything but simple. It is a highly engineered component demanding incredible precision, rigorous standards, and continuous vigilance every single step of the way. From selecting the right materials to calibrating the tools to inspecting the final product with multiple methods.
It's a profound testament to engineering excellence, really, and the human commitment to safety and reliability when the stakes are high.
Right.
The stringent quality demands of NASA for spaceflight hardware needing to survive launch and the vacuum of space converge directly with the safety-critical requirements of the automotive industry. Think ABS systems that stop your car, airbags that protect you in a crash, emergency call systems that summon help.
Yeah, the common thread is unmistakable.
It illustrates a universal truth. In high-stakes environments, whether it's orbiting Earth at thousands of miles per hour or just driving down the highway, there's absolutely no room for compromise, even in the smallest, most unseen details. Every single crimp must be as close to perfect as humanly and mechanically possible.
Exactly. These connections are the silent, invisible heroes holding so much of our technological world together. So next time you hear a car start smoothly or you read about a new space mission launching successfully, maybe take just a moment to consider the millions upon millions of tiny, perfectly crimped connections.
Billions, probably.
Billions, yeah. Connections that were meticulously designed, manufactured, and tested to make it all possible. It truly makes you wonder, doesn't it? What other foundational yet unseen technologies underpin our daily lives without us ever truly appreciating their incredible complexity and the unyielding commitment to quality hiding just beneath the surface?
That's a provocative thought indeed. There's a whole hidden world of engineering marvels all around us, just like this one, waiting to be discovered if you just look closely enough.
Definitely food for thought for your next deep dive. We'll see you next time on The Deep Dive.